Hello and welcome to this next session on data structures and algorithms. Starting today, we will discuss some very simple yet interesting algorithms from the area of computational geometry. Today, we will discuss some properties associated with line segments. For example, how would you know if given 3 points P0, P1 and P2 whether the angle suspended at P0 by the line segments P1, P0 and P2, P0 is clockwise or counterclockwise. That is, how do you find out if P1 lies above or below the line segment P0, P2 and vice versa. So computational geometry happens to be a branch of computer science that studies algorithms for solving geometrical problems, and it has applications in graphics, robotics, VLSI design, computer aided design, molecular modeling, etc. Basically all areas that have something to do with shapes of objects and understanding properties associated with those shapes. So the general input is a set of geometric objects, set of points, line segments, vertices of polygon, etc. Output is either a response to a query about the objects, or in some cases you synthesize new geometric objects. So today's discussion will be largely about query about some objects. For example, do two line segments intersect? In the next class we will discuss an instance of the second kind of output, the synthesis of a new geometric object. We will discuss the synthesis of something called the hull, or more specifically the convex hull of a set of points. You could think of the convex hull as the tightest enclosing polygon around a set of points. For this you might have to drop some points from the boundary of the hull and let them lie in the interior of the hull. Coming back to line segments, we will be interested in characterization of line segments as a convex combination of the 2 points that form the endpoints of the line segment. So let us call these 2 points P1 and P2. So any point P3 that lies between P1 and P2 is understood to be a convex combination of P1 and P2, and the coordinates of P3 are basically convex combinations of the coordinates of P1 and P2, which is alpha x1 plus 1 minus alpha x2 for some alpha between 0 and 1. Y3 is alpha y1 plus 1 minus alpha y2. So more generally we call the point itself to be a convex combination of the 2 points P1 and P2. So P3 is alpha P1 plus 1 minus alpha P2. So we will start with the simplest of inquiries. Given points P0, P1 and P2, and let us say for simplicity's sake we let P0 be just 0 0, that is we set P0 to be the reference point origin, and our question is whether P1 P0 is clockwise or counterclockwise with respect to P2 P0, and this how you depict. As you can see in this figure, P0 P1 is counterclockwise from P0 P2. One might also be interested in whether any two given line segments intersect at all, in which case the inquiry would be more like, do P1 P2 and P3 P4 intersect at all. Let us answer the first question, direction of P1 from P2 with respect to P0. A very fundamental tool to answer this question is to look at the cross product. The cross product is depicted as P1 cross P2 and it is not commutative. So P1 cross P2 is not necessarily equal to P2 cross P1. Now one can understand this cross product as follows. So if P0 is here and we consider a parallelogram with corners at P0, P1 and P2 and the fourth corner being the sum of P1 and P2, which happens to be here, one can interpret this cross product as the area of this parallelogram. However, this area is not commutative with respect to P1 and P2, so we call this the signed area. So the signed area P1 cross P2 is not the same as the signed area P2 cross P1. So one can recall that area of such a parallelogram can be obtained as the determinant of this matrix with P1 as the first column and P2 as the second column. This determinant is x1 y2 minus x2 y1. Similarly, the cross product P2 cross P1 can be written as this determinant x2 y2 x1 y1, and well, this is nothing but x2 y2 minus x1 y1. So one can see that P2 cross P1 is exactly the opposite sign as P1 cross P2. And that is why we refer to this area as a signed area. Now what does this sign actually denote? Well, it turns out that if P1 is clockwise from P2, which is the case here, then this signed area or the determinant of P1 cross P2 is positive. On the other hand, you can verify that the sign of P2 cross P1, which is exactly the negative of P1 cross P2, is negative. So what this says is that while P1 is clockwise from P2, P2 is counterclockwise from P1. So continuing with this same example where we assume that P0 is the origin, the cross product is computed as follows: P1 cross P2 is x1 into y2 minus x2 into y1, and for this specific example P2 is 4, 1, P1 is 2, 3, and this cross product is minus 10. Since the result P1 cross P2 is negative, we have verified that P1 is counterclockwise from P2 with respect to the origin P0. One can immediately see that P2 cross P1 is plus 10, and therefore P2 is clockwise from P1 with respect to the origin P0. How about two arbitrary line segments P0 P1 and P1 P2? So what does this mean? Well, this means P0 P1 and P1 P2 now we will not make any specific assumption about P1 or P0 or P2. Do they turn left or right at point P1? Now it is similar to the previous question of whether P2 turns clockwise or counterclockwise from P0 with respect to P1. So this will be equivalent to the question, does P2 turn counterclockwise or clockwise from P0 with respect to P1, and that is what we have summarized here. The approach will be to check whether the directed segment P0 P2 is clockwise or counterclockwise with respect to the directed segment P0 P1, and that is through this cross product P2 minus P0, that is the first vector that we want, P2 minus P0, that is the vector whose orientation needs to be checked with respect to P1 minus P0. One can generalize the discussion so far to address the following question. We are interested in determining whether two line segments intersect or not. We will answer this question by looking at the direction of turn. We have already seen that if our points were P0, P1 and P2, then the cross product P1 minus P0, P2 minus P0, if it is positive, then we know that P1 turns clockwise from P2 with respect to P0. Now can we use this fact to answer the general question if two line segments P1 P2 and P3 P4 intersect? One would look at different possible angles here, but let me explain the main motivation. The motivation is to see if the points P1 and P2 lie on opposite sides of the line P3, P4, and also simultaneously the points P3 and P4 lie on opposite sides of the line P1, P2. So you can convince yourself that if both occur, that is P1 and P2 are on opposite sides of the line P3, P4, and P3 and P4 are on opposite sides of the line P1 and P2, then indeed the line segments P1, P2 and P3, P4 intersect. There are of course some corner cases that we need to handle. What is the point of intersection? What if the points actually meet at one of P1, P2, P3 or P4? But keeping that aside for the time being, we will answer this question by looking at angles. So what we expect is that if P3 and P4 lie on opposite sides of the line P1 P2, then the angle formed by P3 at P1 with respect to P2 should have the opposite sign as the angle formed by P4 at P1 with respect to P2. In other words, we would expect that on one hand, if P3 was clockwise from P2 with respect to P1, then P4 should be anti-clockwise from P2 with respect to P1. Likewise, we would expect P1 to be anti-clockwise or counterclockwise from P4 with respect to P3, and P2 should be clockwise from P4 with respect to P3. In other words, we would expect the signs of the cross product P1 minus P3 with P4 minus P3 to be exactly opposite to that of P2 minus P3 with P4 minus P3. This has been depicted in this picture. We expect these line segments to intersect if P1 minus P3 cross product with P4 minus P3 is negative, which means P1 turns counterclockwise from P4 with respect to P3, and on the other hand P2 turns clockwise from P4 with respect to P3. This is indeed the case here. It is also possible that the P1 and P2 get exchanged, in which case all we expect is one to be clockwise and the other to be counterclockwise. So what we are looking for in this entire process is the sign of P1 minus P3 cross product with P4 minus P3 to be exactly opposite of the sign of P2 minus P3 cross product with P4 minus P3. Similarly, we would expect the sign of P4 minus P1 cross product with P2 minus P1 to be exactly opposite of the sign of P3 minus P1 cross product with P2 minus P1. One can also consider the case where P3 and P4 are on opposite sides of the line P1 P2, whereas P1 and P2 are on the same side of the line P3 and P4. In such a case, yes, the lines do intersect, but the line segments do not. This precisely is the significance of both the tests. One needs to determine that the cross products have opposite signs for both the pairs P1 P2 and P3 P4. It does not suffice to check for opposite signs only for one of them. Here is the corner case. What if one of the points, say P3, happens to be collinear with P1 P2? In general, what do you expect if 3 points P1, P2 and P3 are collinear? Well, if they are collinear, we would expect that P3 is neither counterclockwise nor clockwise from P2 with respect to P1. It can be neither positive nor negative. So we would expect this cross product of P3 minus P1 with P2 minus P1 to be 0. So the question is that if indeed P1 and P2 lie on opposite sides of the line P3 P4, but if between the cross products associated with P3 or P4 one of them turns out to be 0, then it is possible that the point with the 0 cross product lies exactly on the line segment joining P1 and P2. To check if P3 lies on the line segment P1 P2, we are going to check if the x coordinate of P3 is between the x coordinates of P1 and P2. X3 should be exactly in the line segment or in the closed interval x1 x2 and check if y3 belongs to the closed interval y2 y1. We have very implicitly referred to this specific orientation of P1 and P2 in defining these intervals x1 x2 and y2 y1. We know that y2 is indeed smaller than y1 and x1 is smaller than x2. In general, what you require is that x3 lies in the closed interval min x1 x2 max of x1 x2, and y3 should also lie in this closed interval min of y1 y2 max of y1 y2. If this is not the case, it could mean that P3 is indeed collinear, but it does not lie on the line segment. So let me present a case where P3 is collinear, and here's P3. However, we find that its x coordinate as well as the y coordinate lie outside the range, the closed interval provided by P1 and P2. This is precisely the example. P3 is indeed collinear with P1 and P2, but unfortunately P3 does not lie on the line segment P1 and P2. So please note how we have at times talked about lines and at some other times talked about line segments. As far as points lying on opposite sides is concerned, we talk of their lying on opposite sides of a line. However, when it comes to collinearity, we insist on line segments. So we put together our algorithm for detecting if two segments intersect. Initially we compute 4 directions. Direction D1 is the direction of P1 from P4 with respect to P3. And to remind you what this means, this means that we are pivoted at P3, we look at P1 minus P3 and P4 minus P3. If the cross product P1 minus P3 times P4 minus P3 is positive, then it means that P1 is clockwise from P4 with respect to P3. So likewise we look for the direction of P2 from P4 with respect to P3, direction of P3 from P2 with respect to P1, of P4 from P2 with respect to P1. Note that we have arbitrarily chosen P3 and P1 from the line segments P3, P4 and P1, P2. As homework, you might want to look at the direction of P1 from P3 with respect to P4, basically swapping P3 and P4 here, and similarly swapping P1 and P2 in the directions D3 and D4. You will find that not much will change at all. Now if you find that D1 and D2 have opposite signs irrespective of whether the pivot is P3 or P4, and if directions D3 and D4 have opposite signs, then you are done. If it turns out that any of the four D1 to D4 are 0, which means some 3 points are collinear, then one checks if the collinearity is on the line segment itself. So if D1 is 0, that is if the direction of P1 from P4 with respect to P3 is a 0, then you check if P1 lies on the line segment P3, P4. If D2 is 0, you check if P2 is on the line segment P3, P4 and so on. In either of these four cases, again you know that the two line segments indeed intersect. If none of these are true, which means the directions D1 and D2 and D3 and D4 do not have opposite signs, none of these 3 points are collinear, certainly the line segments do not intersect at all, and the case for this is shown here. As already indicated, direction Pi, Pj, Pk looks at the direction of Pk with respect to Pj from Pi. If the direction is positive, it means that Pk is clockwise from Pj with respect to Pi, and the on segment routine does exactly what we described earlier. You look at the min of xi and xj and the max of xi and xj and ensure that xk lies exactly between the two. You also need to ensure that yk lies in the closed interval determined by the min of yi and yj and the max of yi and yj. Thank you.